In part 2 of chapter 2, we're going to be going over how atoms make bonds with each other. With ionic bonding, here one atom gives up electron, it could be one electron or more than one electron, to an atom that needs it. I'll just put to another atom. And so here, it's really just the electrons being transferred from one atom to another. So if you look at the picture, the one on the left is showing the sodium. So here, sodium has that extra electron. And chlorine just has 7. If we count the little electrons in the outermost circle, only 7 electrons here. So it just needs one more. So now sodium, when it gives it up, sodium ends up becoming a little more positive, and chlorine ends up becoming more negative. Well, because sodium, when it gives it up, it's losing that negativity, so that's why it's becoming positive. And chlorine, because it's gaining that negative electron, it becomes more negative. So after they have either gained or lost an electron, now these are going to be called ions. Okay, so know this word ion. It's an atom that gains or loses electrons to become stable. It becomes an electrically charged atom. Cation. So this is if the atom has become more positively charged. So, and then I'll underline here, this is when the atom loses electrons. And so here, sodium is the one that became a cation. And I put a plus sign with that one. Anion instead. This is the one that became more negative. And so it's formed when the atom gains electrons. So this is for chlorine. Chlorine now has a negative charge. Here's just some more information about ionic bonds. Once again, know that this is formed when electrons are transferred from one atom to another. And so, because one is more positive, one is more negative, well, here the attraction between the opposite charges holds these two atoms together. And that's how we get salt. Alright, so ionic bonds is when electrons are transferred from one atom to another. But here's another bond. This is also to complete the valence shell of the atoms. These are much, much stronger than ionic bonds. So these are formed when atoms share electrons between them. Here in this picture, it shows that hydrogen has one valence electron. Its number is 1. Well, here's the other hydrogen. But hey, they need 2 because only 2 can fit into this valence shell. So they just need 1 more each to fulfill their outermost shell, to complete it. Also here in the picture on the right, it shows how the 2 hydrogens come very close to each other. So here they're sharing the electrons. Here are the ways that these can be written. Now notice that there is a single line between these 2 hydrogens, but how come you see 2 lines between these 2 oxygens here? A single line represents single bond. But so this really means that only one pair of electrons are being shared. But so between the 2 oxygens, 2 lines represent a double bond. So a double bond just means that instead of 1 pair being shared, it's 2 pairs. There are also triple bonds, so that's if 3 pairs of electrons are shared. But yeah, so it's because the 2 oxygens here in this case, they just need more electrons. And so this is explained at the bottom as well. Here it says 1 line between the atoms means just 1 pair of electrons are shared. But if you see 2 lines, that means 2 pairs are being shared. And so this forms a double bond. We're going to see double bonds in the next part of chapter 2. Now, covalent bonds. So we just saw that covalent bonds is when atoms share electrons. But there are actually two types of covalent bonds. Mostly, they're nonpolar, meaning the sharing of electrons is equal between the atoms. But a polar covalent bond, this is if the sharing of electrons is unequal. So this happens if one of the atoms is much bigger than another atom or other two atoms. Here, the good example of a polar covalent bond is water, or a molecule that's formed by a polar covalent bond. So in this case, the red one that we're seeing here, that's oxygen. Oxygen is much bigger and it's slightly negative, meaning that the oxygen pulls the electrons more towards itself. Its protons are actually attracting the electrons more towards itself. The hydrogens, which are the white ones here, those are not able to pull the electrons more towards themselves. So therefore, the hydrogens end up becoming a bit more positive, and the oxygen ends up being more negative. So here, in the second bullet point, this is already underlined for you. Know that a polar covalent bonding is formed by the unequal sharing of electrons. So know that water is an important polar molecule. It's made up by this polar covalent bonding. Another example is SH2, dihydrogen sulfide. And so the same thing with that. Because the sulfur atom is much bigger, it pulls the electrons more towards itself, and the hydrogens are smaller. So yeah, the hydrogens end up getting the positive charges, and the sulfur ends up being more negative. When a polar covalent bond forms this molecule, you end up getting these bendings. So notice how I did these diagonal lines instead of straight. But yeah, so that's because here the charges are repelling each other. Due to these positives and negative ends of the molecules formed by polar covalent bonds, we get hydrogen bonds in between. So here, if you look in the picture, this one is one water molecule. So here in the center is another water molecule, and so are the other ones. The attraction between the negative side of that water molecule and the positive side of this other water molecule that's in the center, this attraction then leads to a hydrogen bond. But yeah, so the hydrogen bonds here are really just the attractions between the separate water molecules. So it would help if you write this. Hydrogen bonds, if we're talking about water, just as an example, hydrogen bonds are between separate water molecules. Now, hydrogen bonds are not only between water molecules, but we're going to say that they form between polar molecules. Right, so next we'll talk about, hey, how can we make larger molecules? And so chemical reaction means when we build larger molecules or break them apart. Now, if you notice in the equation here, this shows sodium chloride, salt. But also here, in this case, it's getting broken apart. Now, in a chemical reaction, in a chemical equation, what you start out with is called a reactant. And what we end up with is called a product or products. Okay, so just recognize these words. Reactant, in a chemical reaction, just means the starting materials. Then the products, as well as what is being formed at the end. Here, these terms are just kind of giving more different names for building or breaking. Synthesis reaction, this is the same as saying anabolism. And so this means building larger molecules. So where it says more complex chemical structure is formed. So yeah, it just means putting together molecules together to make larger ones, or putting together atoms together to make a molecule. building a molecule or building larger molecules. Versus decomposition reaction, this is the same as catabolism. So now this means breaking apart the bonds between atoms or between the molecules, and so making the molecules into smaller pieces. Yeah, so if you would like to write breaking apart molecules. In a chemical reaction, exchange reaction can also occur. So here, this is when the parts of a molecule can end up ending in the other molecule. So here, if we start with, let's say, this AB molecule and a CD, and so here the D ended up getting attached to the A and C with the B instead. Most chemical reactions are reversible, meaning you can build or break them apart. And so here, this is why we see a double-ended arrow here. That's because we can put A and B together, so imagine these are two separate molecules, or they can be broken apart. Next, a little bit about acids, bases, and salts. When these are put into water, they end up separating into their individual parts. So separating into their individual parts is also called dissociation, dissociate. Yeah, so that's because here when we put them in water, these are charged ions and they're attracted to the charged parts of the water molecule. So if you look at the picture, that's what I mean. Here, when we put salt into water, it ends up separating into sodium and chlorine. So here the water molecules end up separating the sodiums away from the chlorines, because here they're just kind of like hugging them away from each other. When salts, acids, and bases separate into these individual parts, these individual parts are called electrolytes. Okay, so I'm going to put here, electrolyte really means, think like individual parts of acids, bases, and salts. All right, next, know the pH scale. pH scale actually refers to the amount of hydrogen ions in the solution, whether we're looking at the acid or the base, but it's in its negative logarithmic scale, meaning the lower you go in this pH scale, the more acidic it gets, and the higher hydrogen. So here, pH of 0, this has very high hydrogen. But when you go up to pH of 14, the other side, so this here means low hydrogen. Okay, so know the range for neutral versus acidic, basic. Well, neutral pH, this is a pH of 7. So here, this has an equal concentration of hydrogen and hydroxide, which is what OH means. It's the pH of water. Then know that acids have a pH of, what does this symbol mean? This means that acids are low, lower than 7, less than 7. Acids have more hydrogen compared to OH in their molecule. For example, here's a good example of an acid, HCl. So when this is put into water, it separates into hydrogen and chlorine. So here, acids have more hydrogen in them, rather than here the hydrogen is not attached to an oxygen. So acids end up donating. They donate hydrogens to a solution, meaning they give them away, well, because they're breaking up into those individual parts. Bases or alkaline molecules. These instead have a pH that's more than 7. Bases instead have more hydroxide in them. So here's just an example, NaOH. Now I'm simplifying these, but here in this case, the base has the OH in it, say sodium hydroxide. And so these instead give off or donate hydroxides to a solution. Normal range of blood is a slightly more alkaline, 7.35 to 7.45, while acidosis occurs when the blood becomes a bit more acidic, versus alkalosis is if it becomes more alkaline or more basic. Well, in either case, our body does not like that. Our nervous system especially cannot function if the pH is becoming too acidic or too basic. Well, thankfully, we have these special molecules called buffers in our blood. These help to resist pH changes. They help to neutralize both acids and bases. Now, what happens is they actually come in pairs. So one part of the pair acts more like a base, and the other part acts more like an acid. And so if our blood is becoming more acidic, the basic part of the buffer ends up neutralizing the acidic one. And so then vice versa. If our blood becomes too basic alkaline, then the acidic part of the buffer helps to neutralize the other one.